field. And we're very happy to have him with us for the quantum chemistry session of QIQT 2022. So Professor Adhikary, yes, I can see your screen. So the floor is now all yours.
So still, I guess it is good morning. Is it? Am I audible to everybody?
Yes, yes.
Yeah. So this is still good morning, and what I'm going to see, the well-known problem in the before starting the Second World War is the synthesis of ammonia, and the synthesis of ammonia was done by some process. It is called Harvard process, and that changed the entire, the so-called civilization, and it make a revolution in the field of not just chemistry but also entire, to move from the so-called primitive world to the first world, because that synthesis of ammonia that actually increased the agricultural production from order of magnitude higher than the existing one, because the ammonia used for agriculture for as a fertilizer. But the synthesis of ammonia, it actually has, I mean, particularly if somebody has gone through 12th class level chemistry, they know that it takes a specific condition. That means you will get optimum production or yield of ammonia starting from nitrogen and hydrogen. There is something like 450 Kelvin temperature. You need certain amount of high pressure. You need iron catalysis, so on and so forth. When you consider all these things, but that was the thing. But the main interest evolved from that point of time. Is there any quantum effect? Is there any quantum effect when actually, let's say, both hydrogen and nitrogen hit the copper surface or iron surface, and that whether the quantum effect controlling everything? So that's a vast community, particularly in the West, who are looking into that phenomena. The effect of surface temperature. Here surface is, let's say, for the ammonia synthesis, it is iron. It can be adsorption of hydrogen on copper, so on and so forth. Any adsorption kind of thing, which is every day, it is used in our day-to-day life. But it is interesting to see that the phenomena of adsorption cannot be explained unless you consider quantum effect, particularly Bose-Einstein or Fermi-Dirac statistics, in a specific and special way of treatment of your equation of motion. So let us see what is the effect of surface temperature on molecule surface scattering. That means molecule is scattered from the surface. Either it is adsorbed or it is chemi-absorbed. Adsorbed has special kind of thing. It can be just physi-absorbed, that means loosely bound to the surface, or it can be chemi-absorbed, that means it is dissociated on the surface, or it can scatter back. So many things happen. So if we move to the next slide, we see what is about the outline of this lecture, and this lecture outline defining the problem. So dissociative scattering phenomena. That means, as I said, when the hydrogen hit on copper surface, it undergo dissociation. Now the question is, with a certain kinetic energy, the hydrogen atom, hydrogen molecule comes and hit the copper surface. Now the question is there any surface temperature effect in the dissociation of H2 on the metal surface? And the corresponding experimental outcome, and those experimental outcome are basically molecular, so-called, extremely sophisticated experiment. Those experiments are called molecular beam experiment. and vis-a-vis theoretical investigation. So phenomena is the dissociation of a molecule on a metal surface, and you have experimental outcome, which are, and those outcome are quantum level. That means state to state, when the H2 come and hit copper surface, when it's scattered back, so it can have inelastic scattering, it can have elastic scattering, and when it have dissociation, that means it will be, so-called Kb absorption or Fiji absorption process. So you have experimental outcome from molecular beam, and that molecular beam experiment are nothing but you have a vacuum chamber and you have a beam of molecule which is hitting on a surface, and the surface is fixed on a particular temperature. Let's say it can be very cold, it can be 1 Kelvin or 2 Kelvin, or it can be 100 Kelvin or 1000 Kelvin. That's the way you design your experiment. And when the molecule scattered back, you will have a mass spectrometer. That mass spectrometer detect the outgoing molecules kinetic energy. And since the Hamiltonian system is a conservative system, so from the the initial kinetic energy of the molecule, and its rotational and vibrational state, because that's the way you fix the molecule. And when it come and hit, then its kinetic energy and potential energy. So the system is conservative, the total energy of the system. And when it comes back, if you can measure the kinetic energy of the species, so from the total energy, if you subtract the kinetic energy of the species, then it's elastic collision or it is inelastic collision, and you can find out what are the rotational and vibrational state or MJ state of the scattered molecule. So that's the background of the problem. Now, what kind of theoretical development we can do? So there can be a Hamiltonian, effective Hamiltonian, and that can have time and temperature dependent, because as the molecule approaching the surface, it will face the interaction between the surface atom and the incoming molecule. So there will be time dependent potential, which is generating because of the incoming molecule on the surface, and you have a temperature dependence from the surface, and that the quantum mechanics is zero temperature formulation. But then to include the temperature, you have to do something, either Bose-Einstein or Fermi-Dirac, through which you can include the surface temperature as a parameter, and then you can consider the coupling between the molecular degrees of freedom and the surface degrees of freedom within linear vibrational translational, that means linear coupling or bilinear coupling between surface and molecular DOFs. And this will be done, let me tell you, within mean field approximation. Because when the molecule come and hit a surface, first of all, the molecule will have 3 degrees of freedom, and with respect to the surface, there will be another 3 degrees of freedom. So therefore, there will be 6 degrees of freedom. So 6 degrees of freedom means already the number of coupled differential equation will reach to minimum 1 billion. So you need to handle such a huge coupled differential equation to get the time dependence wave function of the overall molecule surface scattering wave function, and from that you will do the analysis to find out the outgoing molecule staying either on different vibrational state or different kinetic energy of the molecule. So for that, you need to consider approximation, and we will do this approximation at the mean field level. That means we are not considering the coupling between molecule and the surface beyond Hartree product. That means all other configurations, that configurations consider the correlation between molecule and surface at the higher level, higher order, higher molecular correlation, molecule surface correlation, that will be neglected because that is beyond possibility of at the present level of computer facility, even at the Cray computer. And for that reason, we'll consider very accurate chemical, accurate static corrugation model, Hamiltonian, and interaction potential. And that potential is actually at the level of and the first principle based electronic structure theory, and then we will do the quantum dynamics on the using the interaction potential. The results we will be presenting, that is application of quantum dynamics, QD is the abbreviation, and EH is the effective Hamiltonian, and the potential is static corrugative model. That means the surface atom interaction is, interaction is there, but at the 0th order level, not at the higher level. That means it is within harmonic approximation you are considering. That is what is called static corrugation model. But the interaction between surface atom and the molecule, that is considered at the linear and bilinear. That means you have considered linearly displaced harmonic oscillator or anharmonic terms to consider the interaction. And then we with this methodology, we consider the interaction of H2 and D2, starting from vibrational quantum number 0 and rotational quantum number 0, and hitting the copper surface with index 111. And that kind of experiment is very much possible and at the highest level of accuracy. So we will have experimental data to benchmark your theoretical data, and you can guess where are the approximation and where you can improve. And then you investigate the effect of surface mode vibration. That is the surface mode you have, whether those modes have any role in the interaction between the molecule and the surface. As I said at the beginning, the surface temperature, why the synthesis of ammonia takes a specific surface temperature that is 450 Kelvin, and then you get maximum yield of the production of ammonia. So the surface temperature gives an important effect, and whether that effect is a classical level or a quantum level. And if it is a quantum level, how big difference between classical effect and quantum effect. So that need to be known. And then we find chemical absorption and scattering dynamics for different surface temperature situations. And these are the basic literature which one can go through. The next, I am defining the problem in schematic way. That is, the molecule, you can see the blue diatomic molecule, and that molecule is come and hit the surface, which is represented by a red line. And when it come, then it can have, different kind of process. One of the process is that it vibrational, you can see the number 1, it vibrationally, it can be excited, or it can be rotationally excited, or MJ can be excited, or it can be grazing over the surface. That's why you can have other quantum number N and M can be different starting with respect to the starting N and M quantum number, which are basically 0 at the beginning. So overall, you can see that this is the surface. So that means the red balls are the copper, and they are placed in the position of a crystal with index 111. And then the molecule and come, heat on the surface. And these are the following process it can happen. Now, what is the experimental outcome? So experimental outcome is dissociated reaction probability profile. You can see the magenta curve, that is what is 925 Kelvin, the experiment. And experiment is reaction probability as a function of collisional energy. What is the collisional energy? You give some kinetic energy of the H2 molecule or D2 molecule. With that kinetic energy, it come and hit the surface. And the molecule itself you are keeping, let's say, V equal to 0 and J equal to 0. In the present figure, what I am showing, that is D2, deuterium diatomic molecule, and that is at the V equal to 0 and J equal to 0, and the copper surface is 111. Now, the interesting phenomena is that 120 Kelvin, you can see the curve is like that, and both are S curve, and there is a crossing point. At the lower collisional energy, you can see that lower collisional energy, 925 Kelvin reaction probability. Reaction probability means chemiabsorption. That means it is coming and getting dissociated on the surface. You have higher probability compared to 120. So 925 is higher reaction probability at lower collisional energy, but at the higher collisional energy, you can see it gets opposite. That means broadening happening. That means if you increase suddenly temperature, the reaction probability will not increase, it will decrease. So it is counterintuitive, and that I can tell you, I can vouch you, that is one of the finest experiment done by the group has been written in 1993. Okay, so dissociative chemiabsorption and scattering dynamics of H2D2, that's the caption of this figure, on copper 1,1 surface at non-zero surface temperature to explore the role of surface mode vibration in molecule surface scattering. And surface mode vibration means you have multiple number of copper atom, and when the copper atom vibrates around their equilibrium geometry, it can generate hundreds of normal modes. And if you take a distribution of those normal modes, either through actually Boltzmann distribution, or let's say Fermi-Dirac, because they are harmonic oscillator, you need to consider Bose-Einstein because their operator obey the Bose commutator. So therefore, when you consider harmonic approximation, the you need to consider Bose-Einstein statistics to include the surface temperature in your theoretical formulation. So what is the theoretical formulation? The theoretical formulation tells you you will have a molecular degrees of freedom based wave function, and that molecular degrees of freedom will have 3 coordinates for the molecule itself, and that is small x, y, z, and the capital X, Y, Z are the surface degrees of freedom with respect to the molecule. These are the center of mass position of the molecule on the surface. Okay, so in order to define the molecule, you need to define 6 degrees of freedom, and then you have hundreds of surface modes. That's the product with the molecular wave function, and then something you have that is electron hole pair. That means if the molecule comes on the surface and heat, in that process you can see the sum of the electron moves away from the surface and freely move in the surface, and that also excites the molecule. But in the present lecture, I will try to avoid this part. I will consider only the product of these two, okay, because of the shortage of time. So this approximation is called mean field approximation. If we do not consider mean field approximation, what need to be done? Actually, you need to MCSC answers. That means you have to consider higher, configurations of the molecular degrees of freedom, molecular wave function, and the surface degrees of freedom, surface wave function, phonon modes, so-called, and the electron hole pair wave functions. So if you linear combine them, then it will be MCSCF type of answers. But as I said, even if you consider this mean field level, that already will reach close to 1.5 billion coupled differential equation. So considering higher configurations will be beyond present day computer facility. Maybe that kind of computation can be possible from artificial intelligence line neural network algorithm, or maybe quantum computer. That's where the scope comes for doing some chemistry or physics problem, which is actually already there in place, but you need to find out by using higher technology, quantum computer or neural network kind of artificial intelligence kind of algorithm. But then you need to modify your algorithm and I will show the algorithm, but that algorithm is still within classical computer. But if you go beyond that, then you have need some modification of the algorithm, that I can tell you. Now, what is the Hamiltonian of the system? So Hamiltonian of the system is the Hamiltonian for molecule, which is coming and hitting the surface. And the V0 is the rigid surface. That means surface atom doesn't move. They are fixed at their position. Okay. So that is rigid surface and the molecule interaction. That means molecule and coming and hitting the surface. The molecule and the surface atoms are interacting, and that interaction is called V0. But the surface atom are fixed at their positions. And H0S is the Hamiltonian for solid, and that is the zeroth order Hamiltonian. You consider already they are at their fixed position. Now you consider that interaction due to surface mode coupling. That is the coupling you consider, where you allow that the surface modes are basically vibrating around their equilibrium position. So this is the coupling you consider between the molecule and the surface, when surface atoms are allowed to vibrate around their equilibrium position. And the next two are because of electron hole pair, zeroth order Hamiltonian, and the interaction between free electron on the surface and the molecule, and that is VIELPH. These two terms I will be dropping for our present lecture. So if you consider this is the form of the Hamiltonian, and if you consider the mean field level of wave function, you can see psi product with phi. Psi is the molecular wave function, representing molecular degrees of freedom, and phi is the surface mode wave function, representing let's say hundreds of copper atom sitting on the surface. So when you replace this psi is the capital psi and phi, and the Hamiltonian is this, then you can proceed little bit. Then you including even the electron hole pair, zeroth order Hamiltonian, and the interaction between molecule and the electron on the roaming around on the surface, then you can get this kind of equation, and then you project out the surface mode and the electron hole pair coupling. Just you need to multiply from the left phi vibrational and phi electron hole pair, and then you can come up with the effective Hamiltonian. In the effective Hamiltonian, it gives you the surface degrees, the molecular degrees of freedom, and these degrees of freedom define the molecule with respect to the surface. That means you can see the 6 degrees of freedom, and the interaction between molecular degrees of freedom and the surface, when the surface atoms are fixed at their position. But this is the effective Hamiltonian that you get from considering the surface atom are roaming around, not roaming around, but vibrating around their equilibrium position. And this is the electron hole pair coupling. Similarly, when the electrons are roaming around in a metal surface. So this is basically you can call Born-Oppenheimer static surface. Okay, BOSS, ideal static lattice that at 0 Kelvin. This one is effective Hartree Hamiltonian. Mean field is generally Hartree product emerging from molecular DOFs, surface mode coupling. So here is a possibility of including the surface temperature, but you have to be taking very novel and smart quantum mechanical technique, so that you can include the surface temperature as a parameter, because the quantum mechanics is a zero temperature formulation. Then you have to take help from the either from the Maxwell-Boltzmann statistics of the surface mode, of the surface mode and their states, or Bose-Einstein distribution of the surface mode or their states. That's the way you can include the surface temperature. So how do you do that? So you just expand a Taylor series expansion. Why you can do the Taylor series expansion? Because you assume the interaction between the surface mode and the molecule is weak. Because if it is not weak, particularly you consider the the surface atom mass is at least 2 orders of magnitude higher than the incoming molecule. So recoil effect, recoil effect will be very small. If you hit a wall by a ball, definitely the wall doesn't go back. So that's the consideration. You can, expand the interaction potential around the equilibrium in terms of the normal mode. And this is the linear coupling, and this is the bilinear coupling. Okay. And how do you get the bilinear coupling constant, VK1 and VKL2? That is basically you use some kind of chain rule with respect to the local mode and the normal mode. And those local mode are defined like that R is the distance between the surface atom and the metal atom. That define the, the local degrees of freedom. And the normal mode are basically local mode to normal mode transformation that I am coming in the next page. So using that kind of chain rule, you can numerically calculate the first order coupling and the second order coupling, and these are the normal modes. Okay, and when the surface is not moving around or getting vibration, that not getting vibration, that is called idealized situation, ideal static lattice situation. And this is the situation where the surface atom are allowed to vibrate around its equilibrium at a particular surface temperature. Now you move to the second quantization because you have a normal mode, and since the normal mode you can write in BK daggered and BK, these are bosonic operator, and since normal modes are basically harmonic oscillator, since we know the excitation and de-excitation in harmonic oscillator are bosonic and it follow boson commutator, so therefore you can replace by the bosonic operators. And if you substitute this kind of expression in the previous one, in this expression, you can come to an expression in terms of second quantization, so-called second quantization, where the first term is a linearly displaced coupling term, and the second term you have, and the first term is called vibrational translational operator, because vibrational modes are getting excited because of the kinetic energy of the incoming diatomic molecule. So that's why these terms, the first, and this K is the number of normal modes, number of, surface atoms, and then multiplied by 3 because you have 3 degrees of freedom for each atom. So if you consider 31, surface atom, then you have 93 surface degrees of freedom, and then you have to subtract 3 rotation and 3 translational. So you have 87, something like that, normal modes. And if in the second order, you can see, the first term is basically vibrational operator, and it conserves total vibrational quantum. But in the, the 2 red term, you can see that basically get excited. But if your kinetic energy is not sufficient, it cannot get excited consecutively twice. So these 2 terms, because you are what is your aim? Your aim is to basically see the quantum effect. And if you want to see the quantum effect due to surface temperature and due to normal mode of the surface atom, those are represented by the surface atom in the surface. So you need not to increase the collisional energy very higher than 1 electron volt. Otherwise, it will be approaching to the classical limit because you want to see the quantum effect. So therefore, the first and the fourth term can be neglected because you are not giving enough kinetic energy to get consecutively excited twice. And then, this is, you can write the time dependent wave function for the surface mode in terms of evolution operator, where evolution operator can be written in terms of the zeroth order Hamiltonian, and then the evolution operator in the interaction picture, because it is always customary and theoretically exact, but it will be helpful if you move to the interaction picture of the Schrodinger equation. So therefore, you move to the second interaction picture in this form, and that is very simple. It's a technique that anybody can learn within few days, and then you can write the interaction Hamiltonian. That means this Hamiltonian, even back, if you go this interaction potential, if you look back even, you can see I am working continuously in the first, second, third, and fourth term. How to get the fourth term, in a first principle way. So fourth term in terms of written in terms of normal mode, and then I am written in terms of second quantization, and then I am written in terms of even in a compact form of the second quantization, but in the interaction picture, so that you can avoid the zeroth order Hamiltonian. Once you do that, and these are the term, and you get the modulated normal mode frequency. These are the normal mode frequency of the surface atom, but those normal mode frequency you get from the ab initio calculation, either from VASP or any other modern technique, with a very accurate surface mode vibrational frequency, fundamental frequencies, and those fundamental frequencies are basically modulated because of the second order coupling, and that's what you do here. And then you can again further move, but let us consider first the linear term, otherwise it will be very, very complicated. So if you consider only the linear term at the beginning, and then we will go to the bilinear term, if you consider, as I said, the first order coupling between the molecule and the surface, it's a derivative of the interaction potential with respect to the normal mode, and this can be obtained from the ideal surface hydrogen copper interaction potential derivative with respect to the local mode, and the non-ideal situation, that means you have surface temperature is included at that time, derivative of the copper and hydrogen. Copper is the surface and hydrogen molecule is coming, and they will, if they so you need to consider copper hydrogen interaction, and then alpha and A are the index for the gas atom, and alpha is the index for the metal atom, and then you take a summation over all gas atom, all surface degrees of freedom, and all XYZ, and then you get the interaction potential. And as I promised you that this is the standard transformation that tells you how actually the normal mode and the local mode are connected through a transformation. That is well known. If you have a Hessian matrix, then you can diagonalize, and that is the transformation matrix that diagonalize that the Hessian matrix, and then you give the frequencies, then you get the frequencies, and those will be the frequencies of the normal mode of the surface atom, and these are the local mode and the normal mode, and that's what you get. Now, in order to get that, this had the interaction potential between copper and hydrogen, what you have to do, you have to get a very, very accurate interaction potential. So for that, I collaborated with this Leiden University surface chemistry group, and probably that is if not the best, but one of the best surface chemistry group. And from them, I have taken the parameters of the interaction potential, which is written in this form, and I have used in this derivative of the chain rule to get the linear coupling. So once you do that, and then you have to get the effective potential, you have to take the average over the surface wave function, because already you have the wave function here. I have shown you the wave function. This is the form of the wave function in terms of, because you have to substitute this here and you get the wave function at t0. So once you get it, then you have to take the average over the interaction potential, and which you get in terms of the amplitude, and those amplitudes are alpha. For linearly forced harmonic oscillator, those amplitudes are known, which you can substitute and carry in longhand. And also what you do, this average, you can see that depend upon the initial configuration of the surface atom and initial configuration, and then and which is average over all initial and final state of the surface modes. When you do that, and the initial configuration, what you can do, you can include a distribution, and that define the surface temperature. Okay. Now the distribution here include, and that could be Bose-Einstein. It is most relevant to include Bose-Einstein because you have introduced the harmonic approximation for defining the copper atom interaction potential, and they are replaced by bunch of harmonic oscillators. So therefore, and the harmonic oscillator excitation and de-excitation are bosonic. So therefore, their state distribution, it is better to represent by Bose-Einstein distribution. Or you can check what happened if we take the probability factor by Maxwell-Boltzmann distribution. So then you can longhand, you can carry out, and the alpha here it is a linearly forced harmonic oscillator. You can have analytic form, and those are modified Legrouille polynomial. It is possible in longhand to get a analytic form of the effective Hamiltonian. Now you see the interesting thing. The effective Hamiltonian contain the copper hydrogen interaction potential, and this is square. This is not second order. The first order coupling between molecule and the surface interaction square, and these are the frequency of the normal modes, and this is the switching parameter because you are doing a perturbation theory, so you need a switching parameter which can be plus or minus depending upon the sign of the interaction potential, and then a time dependent a kernel type of term that modulate the potential, and then a temperature dependent term, and that is Bose-Einstein distribution. It will be taking form will be like that, where Z is the partition function, which in terms of H cross omega k kBT. Kb is the Boltzmann constant, and the T is the temperature, which get into as a parameter. So particular temperature you have to do the surface scattering problem, time dependent scattering problem, and then you move to another temperature, you have to do again do the same calculation, and these are the frequency of the surface mode. If you consider Maxwell-Boltzmann, the expression like that. Now we can do both the calculation and see the effect. So very sketchily, I can tell you the rigid surface potential. This is the summary before I go to the result section. I have taken for the rigid surface, that means when the surface atoms are not allowed to move, that potential is Bose potential, and when the surface atom are allowed to move, that potential is called SCM potential. And the frequency of the surface mode are there are different packages from where most common is VAS SFP48 and EDIM and FBD, and those frequency we bought in collaboration with the Leiden group for within cluster approximation, because the frequencies are calculated within cluster approximation, not slab approximation. Okay, there are difference between slab and cluster, that is details of it. And then so in the effective Hamiltonian, as I said, you have normal mode configuration space, you have SCM potential, you have linearly coupled VT model. So that's what so this is the linearly coupled VT model. And then you have where you have the frequency of this normal mode of the surface atom, and you have V0 also. And then quantum dynamic calculation is something called SPO DVR. There is a standard code which actually we have also one code, and Leiden group also have one code for dynamics. For the timing for this calculation, I have used Leiden code just to verify that whether our constructed new theory give the correct result with respect to other theoretical methods and the experimental measurements. So this is the distribution of the normal modes. It is given in terms of terahertz. Hertz and electron volt, something like, I guess, 0.04 electron volt. The distribution, and you can see the vast calculated frequency distribution is more widely distributed compared to the other method. EDM is extended diatomic molecules, some method that gives you the frequency of a cluster of copper containing 31 copper in 3 layers, and they are situated in 111 index. Okay, that's the preparation of the surface. Okay, and when the surface is prepared, and then you try to see the effective Hamiltonian, you consider this is the effective Hamiltonian when you consider Bose-Einstein, when you consider Maxwell-Boltzmann. If you try to see the probability factor, then you can see that effectively you can see the probability factor, normalized probability factor. Bose-Einstein or Maxwell-Boltzmann at 120, and this is this is actually so first let me explain. You see that if you consider EDM, the Bose-Einstein normal mode frequency at lower frequency, it has a higher magnitude, but at the higher magnitude, higher magnitude of the frequency, it has lower contribution. But actually, if you want to see the quantum effect, the lower magnitude of the frequency of the fundamental frequency of the surface mode, those are most important. Let me caution you. So this is very important. They have higher magnitude. If you go the other method, and this method of calculating frequency is most accurate, and at 120 you can see the vast calculated frequency with Bose-Einstein probability factor is much higher probability factor compared to Maxwell-Boltzmann, and that reflects finally, if you consider 120 reaction probability versus collisional energy, you see I have not gone beyond one, effectively after 1 electron volt, our calculation may not be accurate because our approximation is within mean field approximation. We have considered only Hartree product. So our reliability of the data at the highest of the highest accurate level is maximum up to 1 electron volt, because I have considered mean field level approximation. But what is the most important observation here? You can see the strong broadening happen when you consider Bose-Einstein distribution. You see, this is basically this 120 Kelvin surface temperature, and this is rigid surface, and then if you consider this is the rigid surface result is is going like that, and then there is a strong broadening, that means reaction probability decrease if you increase surface temperature. This is counterintuitive. It must be quantum effect. But you see, if you consider Maxwell-Boltzmann, or then there is no effect, or even if you have effect, very little effect. And as I promised you that beyond 1 electron volt, you should not consider my result is how much accurate. Within 1 electron volt, result must be very accurate, and within 1 electron volt, you can see there is a strong broadening when you consider vast frequency of the surface mode, and when you consider Bose-Einstein distribution of those modes of their initial state distribution. Okay, so surface mode really get recoiled. There is a recoil effect. Okay, so these are, greater broadening. If you go 925 Kelvin, you can see this the upper one, this this upper curve, the is the rigid surface. That is, surface do not have any temperature. This is 0 Kelvin kind of situation. But then when you include Bose-Einstein, and if you include that the vast kind of frequency, then you can see that how much broadening happened. Huge broadening happened, and that is essentially such a broadening one can show with a first principle based theory starting from Schrodinger equation without doing any kind of empirical consideration of effective Hamiltonian is the first time, I can tell you. These are various results, and those results are if you consider different kind of frequency taken from different kind of quantum chemistry packages, you see the vast SRP 48 has the maximum effect, and that all the results are 120 Kelvin. That has been shown. Now, if you go back, so Sangeeta, how much time I have? So I guess I have 15 minutes, let's assume. And then if you go and see, and if you make a log plot, then you can see that something very interesting, that at lower surface temperature, the red curve is 1 Kelvin. At lower collisional energy, the reaction probability is very small, but at higher collisional energy, it has higher reaction probability. But as you increase surface temperature, at very, very low collisional energy, the reaction probability increases. But at higher collisional energy, reaction probability decreases. Okay, so that's really counterintuitive. Okay, and I will show you experimental justification is there, and you can understand the Hilbert space I need to consider, that is 180 for Z coordinate. That means the vertical coordinate, the molecule come on the surface, and this is the diatomic two atom hydrogen distance. For that you need this many degrees of this many number of grids. That means number of differential equation, and these are all coupled. And then these are the two surface grid points, and these are the rotational quantum number you need to consider, and these are the MJ. So if you multiply, you can see it will go 1.5 billion. Okay, so that many coupled differential equation, we have solved it actually. Okay, and the time we moved 20,000 atomic unit, and analysis has been done when the molecule is actually 9.08 Bohr away from the surface. That means close to 4.5 angstrom from the surface, sufficiently away from the surface. And optical potential, because this is sort of quantum dynamics people, this is well known, but for the other people this is not known. You see, you cannot propagate infinite time. So when the molecule is away from the interaction region, you just throw it from the dynamical calculation. How you throw? Because you put a absorbing potential with a around that region, your Hamiltonian is non-Hermitian. Otherwise, it is Hermitian. So as soon as the wave function goes there, it gets absorbed. Okay. So this is like that. And this is something, the scattered back wave function, and you can see the rigid surface 1 Kelvin, 120, so on and so forth. But you can see that, at 1 Kelvin, you started with, V0, J0. And if you look V prime 0, that means that is elastic collision. That means you see that this is the red curve, at 1 Kelvin. You can see that its survival probability is decreased sharply. That on the other hand, if you increase the surface temperature, the survival probability is increasing. That means staying probability at V prime equal to 0 is increasing. I mean, really, counterintuitive. Okay. And if you look at the, the elastic collision, that means V prime equal to 1, you can see that 1 Kelvin, as this is not really counterintuitive. You can see as the surface temperature increasing, the excitation happening more and more. Okay. Obviously, there will be a region where the rotational distribution will show maxima, and it is the distribution of the rotational state, and this is perfect as one can expect. As one can expect from a benchmark type of calculation. Okay, that indicate that you have a rotational state where you can show maxima. If the what is the other way meaning? If the maxima of transition probability increasing as the J increasing, that means your results are not converged. So it indicate not only V prime equal to 0 converged, V prime equal to 1, it is converged. That means there is a J prime, let's say J prime equal to 4 to 6, where it shows maximum. Beyond that, it is again the probability of transition going down. Okay. In case of V prime equal to 1, it is between 3 to 4, it shows the maximum, then it goes down. So now come the experiment. Now you can see in case of 120, and if you make a log plot, log of the reaction probability versus collisional energy, at lower collisional energy, you can see there is a sudden increase. But if you do the normal plot, you can see that this is the curve, and this agrees quite well. In fact, our case we have a higher broadening. This is the other theoretical approach, and our theoretical approach curve is Sion curve, and that curve shows sufficiently it broadened. In case of 920, you can see that experiment is there. Experiment is 920K, and this is the green curve. And the other theoretical curve, from the other theoretical group, these are Leiden's group data from their result. They consider thermal displacement, and expansion of the lattice. It doesn't reach any saturation. It's increasing and increasing. But in our case, at present case, of course, there is a difference, particularly at the threshold, but it reaches like a saturation, like the experiment. So qualitatively, it got the trend. Okay, so substantial broadening happened, and moreover, in our case, broadening effect is more. Considering a Hamiltonian from first principle, and including the surface temperature from Bose-Einstein kind of first principle approach, and the trends of 60 quantum 6-dimensional quantum dynamics reaction probability low collision energy region were still not explored. This has led us to re-optimize I mean, there are some difference, this green curve and blue curve. So we need to re-optimize the dynamical parameters focusing at low collision energy. And that we have done for, and this, as I said, this is the reaction probability when H2 hitting on the copper 111 surface. In case of deuterium hitting on copper 111 surface, okay, for an estimation, I can give you, it takes Cray-like computer, this kind of calculation takes actually, and this is a parallel program, actually it takes 40 days. That means for each calculation, for each energy calculation, it takes 40 days in a Cray kind of computer. So this is one of the largest calculation exist in the world. Okay, that I can tell you. And this is for the deuterium where all the dynamical parameters optimized, and 90,000 atomic unit, I guess it is 50 femtosecond kind of thing. Immediately I forgot, but it will be 90,000 atomic unit of time must be 50 femtosecond or something like that. And the analysis point is 9.2 volt, and the optical potential is like that. And this is rigid surface, this is 120, and this is 925, our theoretical calculation. And you can see, if you log plot, you can see the quantum effect. Now, is the quantum effect exist in experiment? Let us see. Let us see, let us see the quantum effect, whether it exists or not. Yes. If you look at that, this is molecular beam experiment, and this is, a log plot versus collision energy. At low collision energy for D2 copper 111, you can see there is a increase at low collision energy, and then it again passing through a minima and then increase. So we are the first to get the trend that you have an increase, at low collision energy. Okay, and that okay, wait a minute, we reach in a wrong place. Okay, so so you can see we have an increase in reaction probability and low collision energy, and that is experimental observation. So we are the first theoretical calculation that shows it. Okay, now these are the survival probability and excitation probability of the scattered molecule, and the molecule is D2 here, and it is scattered from the copper 111 surface, and the trend is counterintuitive. You can see, if you go from higher temperature, lower temperature to higher temperature, you can see that higher temperature survival probability is more compared to, because there is an energy transfer between molecule to the surface, and that's why it is happening, and that's why broadening is happening, and that's why there is a barrier created because of the frequency of the surface mode, and that frequency actually created the broadening. And these are the rotational state distribution that indicate the result are fully converged, because they show a maxima a particular rotational state for vibrational quantum number. This is for inelastic collision, elastic collision, this is inelastic collision, like that. Now, if you go and compare the, in this case, the experiment and other, this is 120, this is 925, and for 925, if you look, these are the other theoretical result that has no saturation, that goes to higher and higher as the, and you see my collision energy range is 0.4 to 1. So within that, I assume my approximation at the level of mean field or Hartree field, Hartree product works well. And you see our 925 reaches saturation, even though the threshold has a difference, but that originate, whenever there is a threshold difference, everybody knows that originate from the potential, and that potential is, Boss potential, that means static potential. So we are not exploring here that one. So that need to be perfected, that I can tell you. And the quantum effect is already there, both for 120 and 925. Now, very fast, I can tell you, and this is some kind of approach when you handle a second order term. The second order interaction potential and interaction, if you consider, and the evolution operator, you have VV and and VT term. And if you substitute the time dependent Schrodinger equation in the evolution form, in the evolution operator form, you get this kind of Schrodinger equation, and then you will have evolution operator for the VT. You get this kind of term for the linearly forced harmonic oscillator, but for the higher order, that means bilinear term, you get this kind of matrix representation of quadratic operator, and then you take a product of that is kind of cluster expansion of the evolution operator, some kind of coupled cluster kind of expansion of the evolution operator. And there are technique, and that technique I will not go through. They are very tedious, but we could able to appear a analytic form for the first time for the bilinear coupling between the molecule and the surface degrees of freedom, and considering, when you consider evolution operator, and then substitute and do all kind of analytic calculations, analytic derivations, and then you get this kind of effective Hamiltonian for the bilinear term. And this you can see in this article where we have already put there in details. And then if you consider again the Bose-Einstein or Maxwell-Boltzmann, the effective Hamiltonian for the bilinear term, where you have time and temperature dependent term based on the partition function, and which include all the frequency of the surface mode, but you consider not only the linear but also bilinear term. And then if you do the dynamical calculation, that is where the Maxwell-Boltzmann and Bose-Einstein get into play in the effective Hartree potential. And then with that term, with those effective Hamiltonian, if you do the quantum dynamics, for the temperature get in as a parameter, and with that parameter, if you perform the quantum dynamics for the 6 degrees of freedom, and we have preliminary result for D2 heating on copper surface, and where you consider, you are yet to develop for accurate calculation for this case. For other case, we have done accurate calculation, and not only dynamical calculation, but also interaction potential. We have taken SCM potential. We have taken vast metal frequency, but here we have considered only so far the preliminary things, because we are on the process of doing accurate things. So rigid surface interaction potential, we have taken normal mode for at the level of EDIM. That means embedded diatom in molecule, that is not as good as vast frequency obtained for a copper cluster. And then we consider VVVT coupling model. That means we have not only considered linear coupling but also consider bilinear coupling, and then EDIM potential, and then EDIM normal mode surface configuration space. And then we perform with our code, in-house code for dynamical calculation, that is called time dependent discrete variable representation code, which is developed in our group. And with that, when we perform, we find that now not only 120, and this is D2 heating on copper surface, not only 120 but also 925. You can see the 120, 120 Bose-Einstein, 120 Maxwell-Boltzmann. For Bose-Einstein case, the broadening is much more compared to Maxwell-Boltzmann, and the black curve is basically rigid surface. In case of 925, the effect is much more pronounced, and in case of Bose-Einstein, you get a crossing basically, because at lower temperature you are getting higher reaction probability, and higher collision energy you are getting lower broadening. You are getting lower reaction probability, that means broadening. That is basically counterintuitive, and that's what we have done the entire this theoretical development to explain this thing which you get from experiment. The greater surface temperature effect for the B distribution. That's the conclusion of this graph. And these are, as I shown you, these are outcome of experimental and theoretical result. Of course, we are still far away for this bilinear case, far away from the experiment, because we have taken not so accurate interaction potential, not so accurate metal mode frequency, even dynamical calculation may be not so accurate. But we are on the process like a linear coupling case, because the formulation is just done. We have tested whether the formulation within approximation level, we have tested that whether it works or not. With that, let me summarize whatever I told. The quantization of surface mode, that is accurate simulation of vibrational frequency at least within level of vast pressure P40 level, and the B distribution, Bose-Einstein distribution of those vibrational states are the two key important factor for broadening of reaction probability at higher surface temperature situation. In fact, this kind of calculation has industrial implications, because industry basically looks at what temperature you get maximum product of different catalysis reaction on the surface. So this kind of theory is, first of all, is a interest of academic interest, and secondly, it has interest also for industry, and particularly the West, the Leiden group, they are highly involved with the industrial houses to predict different kind of reaction at different surface condition, catalysis, and surface temperature. The quantum description of surface vibration lead to encapsulate the enhancement of reaction probability at low collision energy domain, which mainly arise from vibrational quantum effect, and that we got from the experimental evidence. Okay, and this is first time a theoretical evidence we got from a quantum calculation. The effect of surface vibrational mode will be further investigated by incorporating actual surface mode obtained from slab calculation, because in slab calculation you can introduce the boundary condition of the phonon modes. So that's why slab calculation also important. We'll carry out 60 quantum dynamic calculation employing SCF potential energy surface. SCF means the interaction between hydrogen and copper at non-zero surface temperature, combine VT-VV, that means linear and bilinear coupling, with accurate vibrational configuration space. That means vibrational frequencies and vibrational and a transformation matrix between local and the surface mode. That is also very important. And you can see those calculation references you can go through. And let me acknowledge my collaborator in this calculation is Mark Somers, Jogmeyer, and Paul Spring, because they have given me the SCM potential. We have developed our theory here, and they have given us interaction potential. And the Hamiltonian is made, and then dynamics is made. And I also thank Professor Gerhard Krohns, because my visit to Leiden, and that time we came up to this project. And most importantly, I think that is the important, that Mr. Joy Dotto, and he is just submitted, just about to be doctorate. He's finished, and the entire work is done by him, I would say. And Sovik is now doing postdoc work in that area. He's a very smart fellow, but is already away from the lab. But so that's why I can tell you, Joy is the person who did this entire work. And I must acknowledge IACS for the Cray supercomputer and DST for my research grant. From there, I have also several big clusters so that we can do this calculation. And Leiden Institute of Chemistry and IACS for supercomputing facility. So all this, with this, I actually thank all of your kind attention and this thing. And obviously, this is cultivation of science where I belong. So thank you for your attention.
Thank you, Professor Adhikary, for a very, very interesting talk on some very cutting edge developments in quantum dynamics. So are there any questions from any of the participants? You may please raise your hand. You can also type in the chat for that matter.
So wonderful research. I can see the chat box. Output to industry, which kind of skill set, research perspective, etc. need to be developed. How can a researcher try to bridge the academic and commercial space? Okay. You see, the entire last 1 hour. Can you stop this? Stop sharing video. So you see, the development I have shown you last 1 hour. You need the highest of the highest level of quantum mechanics. And you need to know not only just quantum mechanics, but also the quantum statistics. And also you need to know, the packages like VAS that you give the surface mode frequencies and the local mode surface mode, transformation matrix that help you to get the coupling between the copper hydrogen. But the interaction potential calculation, those are basically higher level of DFT calculation that I told you that I have not done it. That has been done by Leiden group. Now, when you predict a surface reaction, which will happen or not happen, and even if happen, you will get a less chemi absorption, so on and so forth. Reaction you can predict. That has obviously industrial value. So you start from quantum mechanics, you start from Bose-Einstein, and then you move to a chemical reaction on a surface, and the chemical reaction happen in presence of a catalysis, and then you predict at what surface temperature it will have a maximum product, at what surface temperature the product will go down. All these things you can clearly tell. So obviously this is close interaction can possible, between industry and not commerce. I would say industry and the laboratory. In India, of course, I would say this kind of industry is not that much. The industrial house do not get that kind of research. They essentially, most of the house takes technology from the West and they just carry out here. But in Europe, as I said, the Leiden surface chemistry group is highly connected with the industrial houses, and they get a lot of funding for doing this kind of research. So this is highly connected with industry, that I can tell you. But for that, you need to know, highest level of quantum mechanics as well as quantum, statistics. So it is not that the quantum mechanics is obviously you have huge interest of, academics here, that how the temperature actually broaden the reaction probability. That means reduce the reaction probability at higher collisional energy of the incoming diatom But the lower collision energy of the incoming diatom, it has a higher reaction probability. That is a strong academic interest. As I told you, theoretically this is the first calculation that shows that higher broadening at low collision energy, and that is verified by experiment. That experiment is done in Göttingen by Woodke, one of my close friend. They do molecular beam surface reaction. This is one side of the academic interest. The other side of the academic interest, there are hydrogen storage you do nowadays. Now, at what temperature you will get maximum storage, this kind of calculation can predict. That I want to tell you. Okay.
There was one more question, probably to Professor Pal, but I think Professor Adhikary can also answer. Which quantum chemistry method will dominate when quantum computers are available?
Okay, there is some misnomers. You see, whatever computer is available, quantum computer or classical computer, or if you use artificial intelligence, your equation of motion are same. You have to come from Schrodinger equation. You have to come, your effective Hamiltonian, whatever you do, and then when you implement in the computer at the code level, then you have to make appropriate changes for getting the data with respect to the classical computer. So it is not that your equation of motion is different. It is not Schrodinger equation, not something else. It is not that. That is a misnomer. Your equation of motion, your effective Hamiltonian will be same. Now you have to make a algorithmic change so that you can implement it in the quantum computer, and that algorithmic change will be definitely different from the classical computer you are using. And then maybe you can do very, very higher level of calculation. Nowadays calculation have a limit. As for example, this calculation have used 1.5 billion coupled differential equation. Beyond that, maybe 2 or 3 billion differential equation, it will be difficult. Now that will be possible in quantum computer, or which is already possible, that is artificial intelligence like neural network or something that is already done, that is already in place. So that much facility you can get, but your equation of motion, your phenomena doesn't change. Since your phenomena doesn't change, your equation of motion doesn't change. That's my feeling.
Okay, thank you, Professor Adhikary, once again. So I see that there are no more questions.